friends, hopefully this will help you with Unit 8, Lesson 3, Graphs of Rational Functions. I know I kind of had a motor in class on Wednesday, so hopefully this will fill in the gaps, or in case you missed something, hopefully this video will help you. So what we did in the first lesson is we were able to identify vertical and horizontal asymptotes and understand how that relates to domain and range. In the second lesson, we did some operations with rational functions, and now the expectation is you can analyze the graphs of rational functions by graphing them without the aid of a graphing calculator. So hopefully you have a copy of the notes either from me or the sub. So I'm not going to read through these at this time, but I am going to go through these 7 steps with each of the following examples. So make sure you have this in front of you. Okay, here's our first example. We need to sketch the graph of the rational function, and we're going to use the following guidelines. So if we look at number 1, we want to simplify f if possible. At this time, you cannot simplify. There isn't really anything to factor, and if you're thinking simplifying means with the denominator, writing that twice and expanding it out, that's not simplifying it, that's making it more complicated. We always want to keep things in final factored form if that's possible. All right, number 2. Number 2, we want to find any y-intercepts. Y-intercepts are easy. We're just going to let x be 0. And when we do the math, we end up with 0. So that means the point 0, 0 happens to be a y-intercept. And at the same time, it also happens to be an x-intercept. So for step 3, to find x-intercept, I let y be 0. And when I cross multiply and do the math, you get 2x is equal to 0, so x is equal to 0, and you end up with that same point. So there's only one intercept, the origin, that is both the x and the y. All right, step 4, we're going to locate any vertical asymptotes. Remember that vertical asymptotes stem directly from the denominator. So x equals -3 is our vertical asymptote. And I am going to denote that with a dotted line, and I encourage you to do the same on your work so that it's very clear that you can communicate to me what that asymptote is. Now notice it's going to be a double kind of asymptote. You've got the same 0 coming up twice. So from our first lesson, hopefully you can expect that maybe the branches might be a little bit wonky when I go to graph. All right, step 5, we're going to locate any horizontal asymptotes. So my horizontal asymptote, because the degree of the numerator is 1 and the degree of the denominator is 2, the denominator is bigger, therefore y equals 0. Now this might be a conundrum for you because you might be thinking to yourself, what's the function? I've got 0, 0, I've got this point right here. How can that possibly be defined on a horizontal asymptote? Remember our formal definition. A horizontal asymptote is defined by what is happening at the ends of the graph, not the middle. So you can have graphs that do cross the horizontal asymptote, but the expectation is that at the end of the graph, I don't know what's happening, but it's going to be going towards 0 towards the end. All right, 6 and 7. Step 7 is that you want to make sure that you have a curve. You don't have anything that is a sharp turn in your rational graph. But really, step 6 is the one that is the most tedious. That's because you basically have to pick points. You have to t-chart it out. How many points do you t-chart out? As many as it takes for you to feel comfortable that you know what is happening with the graph. It might take less for me because I have more experience graphing these. So here is what I'm going to start with. If I know that my vertical asymptote is at -3, then maybe I want to see, well, what is happening at -4? So when I put -4 in here, I'm going to get -8 over -4 plus 3, which is -1 squared, which is 1. So I'm going to get the point -4, 8, -8. Okay. All right. Maybe I want to figure out, well, what is happening here at -2. And at -2, that's going to give me a -4 on top with a 1 on bottom. So the output's -4. So at -2, I am at, and you're like, what's going on here? All right, let's see what's happening at -1. All right, at -1, when I do the work, I get a -2 on top. I get a 4 on bottom, so I'm left with a -0.5. Okay. Well, as I kind of keep going, let me see what's happening at 1. When I put in 1, I get a 2 up top. I get a 4 squared on bottom. So that's going to be 2/16 or 1/8. So it is just right above. And maybe you decide you want to happen what's happening at 2. At 2, I have a 4 on top, and then I have a 5 squared on bottom. So I have a 4/25. So it's getting a little bit higher, not so much. This is where you have to decide. You can keep picking 3, 4, and 5. But if you understand that the horizontal asymptote means that the end behavior has to go to 0, maybe it goes up a little bit higher. I'm not certain. But what I do know is that from this point, it's just going to keep closer and closer to that vertical. And then at some point, this has got to get pretty close. Now, again, this is a sketch. It's not an exact graph. Maybe I don't have the peak at just the right point. But I do know that if my asymptote is at 0, that the end behavior, maybe it comes up, but it's gradually going to have to come back down. For me personally, on this side of the graph, on the left side of the graph, I kind of know what's going on because I'm bounded by this horizontal asymptote, that vertical, and I do not have any more x-intercepts on that side. But if you need to, pick -5, pick -6, pick points to see what's going on. But what is happening is I have a branch that's doing that. Remember step 7, that you are making continuous curves. And for those of you that want to see it a little bit more exact, here is what it looks like exact. So again, in this region to the right where you see the arrow to the right, like where you see 1, it doesn't get real high, but it starts going back to 0. So if you need a, looking at the numerical, you can see the same thing. At 2, it's at 0.16. At 3, it's at 0.166. At 4, it's 0.16. And then at 5, it starts going down to 0.15. So it's right around where x is equal to 5 that it kind of starts decreasing back to 0. That's kind of where your hump is. But these numbers are so small that it doesn't even really look that significant. All right, let's go to problem 2. We go through the exact same set of steps. First thing we look at is on -3 over x squared minus 3x. Is there a way to simplify? And no, you cannot simplify this. Now, you could factor the denominator. So it is x times x minus 3, but you don't have a common factor in the numerator and the denominator, so it isn't going to reduce. All right, let's look in for our y-intercepts. So we're going to let x be 0. And what you end up with is undefined. What this means, it does not mean that the graph is undefined. We were trying to find y-intercepts. This means that there are no real y-intercepts, so this graph is never crossing the y-axis. Step 3, let's try to find x-intercepts. So when I set -3 over x times x minus 3 equal to 0, I end up with 0 equals -3. Again, this doesn't make any sense. 0 does not equal -3, so this doesn't mean that the graph is undefined. It means that there are no x-intercepts. This graph never crosses the x-axis. This graph doesn't ever cross the y-axis. These kinds of problems are a little bit of a pain in the patootie because you have to determine, well, then how am I going to graph? It's going to make step 6 when we do our t-charts a little bit more cumbersome. All right, step 4, vertical asymptotes. Remember, those come directly from the values that cause us to divide by 0, provided you have reduced by any common factors. So I have x equals 0 and x equals 3 as my vertical asymptotes. So I'm going to denote that again by dotted line. Okay. In terms of horizontal asymptotes, the degree of the numerator is 0. The degree of the denominator is 2. Therefore, y equals 0. Since the degree of the denominator is bigger, y equals 0. Okay, is going to be my horizontal asymptote. Now notice we had no x-intercepts, so this graph is not going to ever jump the horizontal asymptote. The only time it's going to jump the horizontal asymptote is if there is a defined point on that horizontal asymptote, and we've already discovered that that's not the case. All right, friends, let's go t-charting. All right, so let's say that I want to see what is happening at -1. Okay, at -1, I'm going to have a -3 in the numerator. I'm going to be using this. You can use either this denominator or this denominator. I'm going to have 1 plus 3. So I get -1, -3/4 as a point. Okay. I'm going to put in 1. If I put in 1, I have -3 over what? 1 minus 3 over -2. So that equals a positive 3/2. Let's see, you might want to know what's happening at 2. I have -3 over 4 minus 6. 4 minus 6 is a -2, so I also get a 3/2. Okay. Let's see what's happening at 3. Oh, we have an asymptote there. Let's see what's happening at 4. I get -3 over 16 minus 12, which is 4. So I get another -3/4. So I'm kind of seeing some symmetry here. I personally, at this point, can tell you what's happening in the graph. Because of this point over here, and I know that it is bounded by that this horizontal asymptote and this vertical asymptote, I know that I have a branch here. If you do not feel comfortable with that, then you might want to pick values like -1/2 to see what's happening, or -1/4, or -1.5, or keep going. Get it together. -1.5, or -2, or -3. You might need to pick more points to convince yourself that that's how the branch goes. Also in the middle, I know that this region is bounded by these vertical asymptotes and that horizontal. So I know it's got to be going near here. And it comes down, I'm not really sure what that minimum value is going to be, but I know that it's probably going to come down somewhere in that neighborhood. And then on the right side, just knowing the little bit, prerequisite information I know about rational functions, I'm going to have a branch on this side. And again, if you are uncertain, like Mrs. Knapp, I would have never guessed that that branch is there. Then you need to pick more points. You might want to pick what is happening at 3.5 or 3.2 or at 4.5 or at 5 to get more points to kind of, let me do that in black, to get more points so that you can see the curve of what's happening. That's the only difference between what I did through thought and what you might need to do more with points. Since this is a video and arithmetic is kind of cumbersome, you are on your own to do that on your own, but that is the only difference. If you're sitting there going, how did she know the branches were that way? Well, pick more points and hopefully you will start to see a bend, a bend, a bend. And if you understand how asymptotes relate, that the graph is going to get really close to those, but not go over them, then life is good. And just to remind you, if you're wondering, well, why didn't this part, how do I know that like this part, this branch right here doesn't go over the horizontal asymptote? We had no x-intercept. So that piece of information was helpful. All right. There are more. I could do example after example after example because rational functions, they're all different. So please make sure you go to page 346 and 347 in your text and look for more examples. And for those of you that want to see on that last problem a more accurate graph, this is an example of the graph. And if I make a T-chart for you, notice how you can see the different values. Those of you that have a TI Inspire, if you go to menu and you go to number 2 table and edit table settings, if you wanted to check your answer, and again, check, because if you're graphing these off the get-go on your graphing calculator, you will not have one on your test and it's a crutch. You can put in that the table step is like 0.5, so that would get you X values that are in between if you need more of those values. All right, let's move on. We have one more example, and this one has a slant asymptote. Earlier in the first lesson, I told you that we have vertical asymptotes, we have horizontal asymptotes, and then we have cases when the degree of the numerator is bigger than the degree of the denominator, then we have cases where we do not have a horizontal asymptote. If the degree of the numerator, which in this case is 2, is a degree 1 or, if the degree of the numerator is exactly 1 more than the degree of the denominator, so that difference is a degree of 1, then you have what is called a slant asymptote, and some books and websites might use the word oblique instead of slant. Those are interchangeable. So this is how you find a slant asymptote in words. Those of you that prefer more symbolic notation, if the degree of the denominator is greater than 1, so again, that should see if the degree of your denominator is greater than 1, and the numerator, oops, I thought I had it on highlights, and the numerator is exactly 1 more degree than d of x, then you have a slant asymptote. Okay, how do we find them? You find them using long division. So in my previous problem, okay, we were looking at the function y equals x squared minus x over x plus 1. Okay, so we'll come back to this graph in just a minute. Okay. All right, let's do some long division. X goes into x squared, x times x gives me x squared, x times 1 gives me x. Remember when you do long division that you have to change the signs. So those cancel, leaving me with a negative 2x. I do not have a constant to bring down, but since the degree, here I've got a 2x. Oops. Sorry about that. Here I have a 2x. The degree of this is x. That's not a remainder yet. All right, so now I have x can go into negative 2x, negative 2 times. When I distribute the negative 2x, I get negative 2x minus 2. Please remember you need to change the signs. So I'm left with a remainder of 2. So I have 2 over x plus 1. If we notice from the previous slide, and I take this graph, and let me make it bigger, notice that the slant asymptote has a y-intercept of negative 2. And I want you to notice that at negative 2, if I do my rise over run, I'm going up 1 over 1. I'm going up 1 over 1, up 1 over 1. And I am getting my slant asymptote. So the equation of that is x minus 2. And notice how in my long division that the part that does not include the remainder, that right there, my friends, is the equation of your slant asymptote. So in other words, you're going to do your long division. You're going to pull out basically you're pulling out a factor of x plus 1, and it might not go in evenly, but you're still taking out that factor. And the part without the remainder is going to be the equation of your slant asymptote. So let's do our last example for the day. Okay. Let's do g of x is equal to 4x squared minus 2x plus 1 over x minus 1. Okay, let's go through the steps. 1, can I simplify? The numerator does not factor. There are not 2 factors of 1. Even when I combine with 4, that's going to yield a negative 2. So I cannot simplify. I know I've not done any examples where you can, but please make sure you do, and please make sure you look at those pages I recommended for the examples. Okay, we cannot simplify. 2, let's find our y-intercepts. That's pretty easy. It's going to be 4 times 0 squared minus 2 times 0 plus 1, all over 0 minus 1. That cancels, that cancels, that cancels. So my y-intercept is going to be 0, negative 1. Okay, let's find x-intercepts. So when I find x-intercepts, I have 0 over 1 is equal to 4x squared minus 2x plus 1 over x minus 1. So I have 4x squared minus 2x plus 1 equals 0. When I do quadratic formula on this, I get x equals the opposite of 2 plus or minus the square root of negative 2 squared, which is 4, minus 4 times a, which is 4 times 1, all over 2 times 4. You should not have to go on any further. Hopefully you can notice that 4 minus 4 times 4 is going to yield a negative number. that means the discriminant, or this part of the quadratic formula, is going to be negative, which means you have no real x-intercepts. Okay. Step 4, vertical asymptotes. As a reminder, that always has to do with any values that cause us to divide by 0. So x equals 1 is my vertical asymptote. Okay. Fifth step, I am going to look at the horizontal asymptote. Well, the degree of the numerator is 2. The degree of the denominator is 1. Therefore, I do not have a horizontal asymptote. However, you need to go one step further. The degree of the numerator is exactly 1 more than the degree of the denominator. And on a test, nobody's going to be saying, hey, there's a slant asymptote in this problem. You need to understand when they occur. So it occurs when the degree of the numerator is 3 and the denominator is 2, or the degree of the numerator is 100 and the degree of the denominator is 99. I might have just said that wrong. If the degree of the numerator is 100 and the degree of the denominator is 99. Whenever the degree is a difference of 1, then I have to see if there is a horizontal or if there is a slant asymptote. In this case, there is. So let's do some long division. Okay. I need to take x minus 1 and I need to put it into 4x squared minus 2x plus 1. Okay. So x can go into 4x squared 4x times. So that yields 4x squared minus 4x. Make sure I change my signs. Bring down the 1. Okay. 2 times x gives me 2x minus 2. Make sure you change your signs. So I have a remainder of 3 over x minus 1. Okay. But 4x minus 2 is going to be my equation of my slant asymptote. All right, so let's graph that. I'm going to go to 2. And I'm going to go up 1, 2, 3, 4 over, okay, 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4, 1. All right. I chose kind of an especially kind of harrowing problem. So I'm going to let you can do the calculator work on your own. I'm going to give you some values that I've already prepared for you. So here's my T-chart for step 6. I picked -2 and I got -7. I picked -1 and I got -3.5. I picked -0.5 and I got -2. I picked 0 and we already knew that and got -1. And then I picked +0.5 and I got -2 again. So what I saw is I kind of saw a little bit of a turning point here, like a place where it goes back and forth. So that convinced me I have enough going on. So at -2, I'm at 1, 2, 3, 4, 5, 6, 7. At -1, I'm at 1, 2, 3.5. At -0.5, I'm at -2. And then at half, I'm back at 2. So what's happening is it's making a branch that's doing this. Okay. All right, next I wanted to see what is happening on the right side of that vertical asymptote. So it's hard to see as I'm doing this on a video. I want to know what is happening on this side of the graph, what's going on here. So again, I picked some more points. I'm going to do that T-chart on the right side since I've got a split screen. So on the right side, these were the points I picked. I picked what's happening at 1.5, what's happening at 2, what's happening at 2.5, what is happening at 3. And at 1.5, it was at 14. At 2, it was at 13. At 2.5, it was at 14. And at 3, it was at 15.5. So again, I saw these values come up again. So here's what's happening. It is way up high. In fact, I probably need a better scale. But in this region right here, way up here, you have another branch doing that. So for those of you that want to see it using technology, here is what the graph of it looked like. And I had to zoom in a little bit because of this point right there. That is the point 213. And then at 1.5 and then at 2.5, each of these were at 14. And so that's how I knew. So here is our vertical asymptote that we had, and there is my slant asymptote. Okay. So hopefully this was a helpful lesson for you. Sadly, you need to practice. Once you get good at it, and the most tedious part of this is step 6. It's picking those points and determining, well, how many do I need so that I know what's happening in the graph? And really that comes with experience and practice. So good luck. Your assignment is page 350. Look at numbers 1 to 11 odd, 13 to 41 every other odd, 43 and 47 to 59 every other odd.